Okay, good afternoon everyone. My name is Hans Verkouw. I'm Dutch. Goedemiddag allemaal. And I live in Norway. And I've been working on Video4Linux in the kernel for something like 11 years now. And since the past year, I've been one of the Video4Linux maintainers of the subsystem as well. One of the areas that I've been very active in is actually developing frameworks to help driver development. If I go back, say, about 6-7 years ago, there was very little. And that led to very complicated drivers, very messy. And one of the things that I wanted to do was to add support for really complicated hardware. And the framework was a real blocking thing. I was basically missing frameworks. So I've done a lot of work on that. And this is basically this presentation is based on a 4-hour deep dive into Video4Linux. I hope it's not going to take 4 hours. I think some people get mad if I do that. So I've tried to condense it into about a 50-minute talk. What does Video4Linux do? Actually quite a lot, besides video capture that you would expect. It can also do codec support. It has video output. It can do vertical blanking information, teletext, widescreen signals, the closed captions in the US. Also does radio. Basically, radio is TV without the video. So Video4Linux has support for tuners. That's the only bit that's actually being used. Support for radio data system has also been added. So that's the things like traffic information and what sort of program type you're listening to. We also have support for radio modulators, radio transmitters. Software-defined radio, that's going to be brand new. It's upcoming in 3.15 unless something special happens, but I would expect it to be merged quite early. We have support for low-level devices, so if you have, say, an HDMI transmitter chip, then you might want to control that on a lower level than you would normally do. And there is device topology discovery. If you have a really complicated system with lots of receivers, transmitters, dynamic routing internally, then you need a way to expose it. I'm not going to talk about the last two. As I said, it was 4 hours, the whole deep dive. I'm not going to manage that. What does a typical driver architecture look like? One thing to remember for video capture in particular, it's always a constellation, almost always a constellation of devices. You have some bridge driver, which is generally controlling a DMA engine. And then you have video receivers, video transmitters, mixers, audio stuff in the loop, video improvement, the interlacer scalers, basically anything that a hardware engineer can think up. When it comes to video, you have to implement, and it's usually a separate block. Hardware designers are incredibly inventive, so we had to come up with a way to make it really generic. But the thing to take away with is video hardware is typically a constellation of all sorts of drivers that have to work together. How do you figure out which of those low-level, we call them sub-device drivers, are necessary? That's generally based on a USB ID, PCI ID, your platform device tree, well, whatever you need to do it. Typically, the bridge drive is the one that's responsible for loading all the sub-device drivers, get everything into order, and then everything is initialized. The device tree model that has been introduced, which is basically a textual specification of what's in your system. Problem there is that that's great, so you can actually enumerate and have this device, and that's there, and these are the interrupt lines or whatever. How does everything fit together? The problem is that the order in which drivers are loaded is random. Well, not quite, but you cannot rely on the order. So what normally happens for USB and PCI devices is that the USB or PCI bridge drive is loaded first, and that loads the rest. That doesn't work in the device tree, and some work has been done in recent kernels to help go around that, and that's the V4L2 asynchronous mechanism. Basically, the bridge drive is just waiting till everyone has loaded, and the sub-device drivers wait until the bridge driver has been loaded, and they all wait for one another until everything is there. Then the initialization takes part. If you need that, V4L2 async, look it up, there's a header, source, and that should help you. I actually do a little bit of resources first to get it out of the way. Public API is available here. I'm also building every day the latest version, so if additions have been made to the API specifications, then they will end up here. So this is the public API. It's always kept up to date, by the way. If someone makes patches that changes the API or adds stuff to it, they have to provide documentation patches as well. For the driver stuff, we have two text files, V4L2 framework, which explains all the main frameworks, and V4L2 controls. That is for the control handler. I will talk about it later. Again, any changes that are made into those internal APIs, they have to be documented there as well. For the Video Buff2 framework, there is no proper documentation yet, unfortunately, but there is a header which has pretty good comments. Upstream Git repository can be found there. There is a Video4Linux utilities. They are found here. Very useful utilities. And you have the mailing lists and IRC channel, which is where you can reach us. So when I was preparing for this talk, I was actually thinking that it might be nice to actually show some code. And one problem is that when developers start on a Video4Linux driver, they generally work from some sort of a template driver, and they always pick the very worst one, which has the worst possible conventions. So I decided, okay, let's just write a skeleton driver. I chose a PCI skeleton driver. By the way, if you just Google for V4L2 PCI and skeleton, you should find it immediately. It should be on the top of your list. It's currently an RFC, but I hope to get it into the kernel soon. I also plan on writing a USB driver. USB are hot pluggable, so there are some special issues with that. And it would be nice to have a good example driver that people can just take and then strip out what they don't want, add what they need. And I actually have code. Yes, so that's something nice, I hope, at least. I hope it's all readable, which is why so again, if you can't read it, Google PCI V4L2 skeleton and you'll find the full source code. It's a bit condensed. I have omitted some of the error stuff, error handling stuff, because otherwise it would be really not that interesting. So don't use this as the basis. Look up the actual posted patch. Oh, PCI device. This is standard PCI driver. PCI devices here. You have some PCI IDs, all the boilerplate code. So the first thing of the framework is that we have a top-level structure, V4L2 device. Sadly, if there's one thing I would like to do over is rename that structure. It's not really a device as such. It's more like the root structure from which you can reference all the other stuff that is going on. My apologies. I actually tried to change it in the kernel, but it was rejected. They didn't want to have all the renaming going on. So. My fault. I came up with the name and I've been sorry ever since. So you have a PCI device, so you need a probe. The probe basically does some PCI stuff. It allocates a top-level structure containing all the state. And it registers the V4L2 device. Again, very bad name. Originally, it would actually register to some global array list. In the end, we realized it isn't necessary, so the register is really an init, and the unregister is more like a cleanup. Again, tried to rename it, wasn't accepted, so we're stuck with it. It basically just gives a pointer to your PCI device as the top-level device that's there, and it will use that to create some proper readable name of the device instance and set up some internal stuff. So that's step one. So struct V4L2 device, top-level struct, bad naming. It also contains a list of I will occasionally mention sub-device. So those are the devices like receivers, transmitters, mixers, whatever. I don't have the time to actually show how it's used. But you can imagine a top-level structure, it needs a list of those devices so it can be accessed. So that's also contained there. A sub-device like, say, an HDMI receiver, it might report back when it sees a hot plug event, or it has to so there's some notify mechanism to go back to the bridge driver. V4L2 device also has a release callback, and that will be called when the very last device reference goes away. Not really that relevant for PCI. Well, I know there are hot pluggable PCI cards and systems. In practice, nobody has ever tested it, and I can guarantee that, or at least for Video4Linux, and I can guarantee that it won't work for Video4Linux drivers, PCI drivers. USB devices, much more common, and they really are hot pluggable, so the support for that is much better. And the release callback is ideal. You can just hook it up, and it will really be called when the very last reference goes away. It's the one you should use. If I make a USB skeleton driver, that's what I will initialize. Next framework, video device. Now that one has been around since the very beginning of Video4Linux. It's the only one that has been around, so everything else is new. But this is the basic structure representing the video node, /dev video 0, or can also be used for VBI, vertical blanking, radio, software radio that's coming up. And that just does all, it actually creates a node and sets everything up. But it has a whole bunch of useful fields that you have to fill in. That's this one here. And this is a bit silly. I mentioned that the V4L2 device, it has a release function. And it's also new. So in the old days, you need a release function as well, but that was hooked up to the video device because that's the only one that was around at the time. In this case, video device is just embedded into the top level structure, but you are forced to give a release function. If you don't, it will bug, it will call bug on, and it will be rejected. And, so this is just a standard function that does nothing. There's nothing to do here. I would like to allow this to be null if you do nothing, but it's sort of historically some of the drivers they never filled in, and there was no release code at all. So this forces you to at least think about it. You have a bunch of file operations, read, write, Ioctl, all that stuff. Ioctl support is in here. I will show that later. We also have a log. I will also have some more points on that later. And you give it a pointer to the top level V4L2 device. So that way it can find its way back to the top level structure where it can do whatever it needs. If you have a card that is capturing analog TV, then you have to fill in the TV norms that are supported. So NTSC, CCOM, PAL, whatever your hardware supports. Prio, we have some support for priority. So it's annoying, you know, you're capturing and you're recording something and some other application starts changing the channel while you're doing that. You want to be able to block that. You want to say, hey, I'm recording. Nobody else messes with my settings. There is some support for that. That's called priority Ioctls. The reality is perhaps 5% of the drivers implement it. So obviously applications won't use it because there are no drivers that implement it. For all the framework reorganization, I actually made support for it that it's done in the core, but you have to set this bit. That's for backwards compatibility. Not all the drivers are yet using the very latest frameworks. I'm working on that, and actually I hope that probably this year the whole bit will go away and then it will be enabled by default and all the drivers will have that support. You give it a pointer to the skeleton structure and you register it. So we have file operations, as I mentioned, that you pass in. So there's an open function, release function, and an Ioctl function. So we have Video4Linux has a huge number of Ioctls, something like 80 or 90. There's actually a structure, and that's this one here, where every Ioctl has its own function, its own callback. And the core will actually take an Ioctl, will figure out which Ioctl it actually is, and call the right callback here. And the function, and so you need to provide a pointer to video Ioctl 2, which is the core function that does that work for you. So you don't have to do that yourself. You just give that pointer and you're done. I'm actually thinking that in the end this might disappear and it will always call that function because everyone should be doing that. Open and release, these are also boilerplate functions. When you open a video node, V4L2 file handle structure is created. If you don't have to do anything special, then you can use these boilerplate functions for you. One of the first functions that every Video4Linux driver needs is query capabilities. So this is sort of the start, the first function you add, query cap, fill it in, and you use these standard functions, and you have your first Video4Linux driver. It doesn't do anything yet, but it will function. Our video device, it represents video, radio, vertical blanking. Also sub-devices can use it as well. It typically represents a DMA engine. So what do you use it for besides controlling? So selecting inputs or outputs or setting brightness and stuff like that. So you control what it's doing. It's primarily also used for actually transferring the video. For that there is a Video4Linux framework, and I will get to that later. You have the pointer that you have to set up for all your Ioctl operations that you support in this driver. File operations, again the Ioctl, the open, the release, you may have read, write, memory map. And there is core logging support. So basically there are two logs that are available in the core. One is the one that I had set up here. So that's just a top level mutex. If that is set, then it will serialize all the Ioctls. If it's not set, then you have to do all locking yourself. My experience is that locking is hard. Nobody ever did it right the first time, particularly when talking about the Video4Linux driver was perhaps 20, 30 Ioctls, and you have to figure out when do you need to lock, when shouldn't you lock. Very few people can get that right. It's also very hard to review. So what we did, we added that serialization lock. If you set it, then every Ioctl will be serialized. Only Ioctls, not file operations. So in the open and the release and read write, you still have to lock yourself if necessary. Which is great, but for certain devices, particularly USB devices, when you dequeue, when the buffer is ready, so a frame has been captured, you need to dequeue that quickly. So there is a dequeue Ioctl, you need to be able to, it shouldn't have to wait. If the frame is there, it should return. But for a USB device, if you want to change, say, the brightness, then you send a USB transfer, and that can take a long time. But those are slow operations on a USB, or it can be a slow operation on a USB device. So if you have a top-level serialization lock, then you change the brightness, then you can't dequeue the buffer because it's waiting for the brightness to change. Not a good idea. So for those cases, there is also a lock for the Video4Linux queue, which is, I will talk about it later, that's the DMA engine. And then that lock will be used for those streaming Ioctls. So they're separated from the others. And as I said, for file operations, you always have to do it yourself, for the non-Ioctl file operations. I'm very happy with it. Not everyone agrees. Some people really want to do their own locking. My experience is it's just so hard to get right. Next step, so you have a video device, capture cards, they have inputs. Generally could be an S-video, composite, HDMI, TV, whatever. You need to enumerate that because user space has to know what it is. So you have enumerate inputs. That's this function. So this card that the PCI driver that they made, it has an HDMI input and an S-video input. So the one is high definition, the other is standard definition. They handle differently, so it's interesting to see how that works. So we see here some different handling for that. You have to mark in the capabilities whether it's standard definition or high definition. You set an input. Well, it's pretty straightforward. The main thing is that TV norms field that I mentioned before, which tells the system which TV standard definition standards, that doesn't work. Standard definition formats are supported for this input. If you have an HDMI input, then that should be set to 0 because it's not valid. It's not a PAL or NTSC input. If you have an S-video or composite connectors, then you set it up. So that's a little thing to keep in mind. Setting up a standard. First off, if there is, so if you try to do this for an HDMI input, then you should return no data because it's the wrong input for something like that. If it's the same standard that it was before, you just return 0. Why do you do that? Some applications are stupid and they just call set standard multiple times with the same standard. Problem is that you cannot typically change standards while streaming. I'll come to that later. But if you would block it, you say, hey, I'm streaming, so I return an error. Then applications that just try to set the same standard while you are streaming, they will be blocked as well. And some applications do that. So if it's the same thing, just accept it. Get standards, well, that's trivial. Query standards, that's basically saying, okay, what standard am I seeing? I'm just looking at the input. I have this receiver chip that's usually able to detect whether it's PAL or NTSC. And well, that's something you have to fill in because that's very hardware dependent. And that just gives back what you are actually detecting. One thing, query standard, it does not change the standard. It just detects. If you have a pipeline, a video pipeline from input to output, and you've set it up and you're streaming, you cannot just change the size of the format midstream. So PAL is 576 by 720 by 576, NTSC is 720 by 480. If you change between one or the other, suddenly your frame sizes increase as well. And all those frames are DMA'd into memory. So if you have allocated a buffer for NTSC and suddenly you get data for PAL, you're having a massive buffer override. So query data should not actually change anything. This is actually any hardware, if there are any hardware engineers here, if you have a DMA engine for video, you really have to make sure that you always stay within the bounds of your DMA area. Hooking up, say, an analog signal VGA cable, it's amazing the shit that you can receive there. You can actually get, say you have 640 by 480, very standard VGA. If you're unlucky and you get a bounce on the VSync, you may get 640 by 800 because the VSync telling that, hey, this is the end of the frame and here a new frame starts, that can just disappear. We've seen that. So suddenly you can really get frames that are larger than you're expecting. If your hardware cannot be forced to constrain those DMA transfers, so it's just looking at the VSync instead of actually having a counter and seeing how many data has been transferred, then all hell breaks loose. You just get random buffer overrides. And there are chips that do not check for that. Actually, we had to work around that by actually putting the memory for the buffers at the ends of the DDR memory. But if you do get an override, it just goes to the bit bucket in the sky and it just disappears. Luckily, there is no address wraparound or anything. That would be really bad. So that's the way we had to work around it. The big difference between video transmitters, there you control what you're getting. You can actually set up what you're doing and you know you should not have to take care of weird stuff coming in. For receivers, it's quite different and it is just utter crap what you can get there. So high definition, it's all a little bit more complicated. You have lots more to set up there. I'm not going into too much detail, but the basic idea is similar. One thing that's new, you have capabilities. So your video receiver hardware, it has constraints, a minimum pixel clock, maximum pixel clock. What can it handle? So you set that up. And after that, it's the same. You have function to set stuff, set it up. Function to get the current timings, enumerate the available timings, and also query the timings. What are you seeing on the video input? Again, querying should never change the actual video settings. It just queries what you're getting. How am I doing for time? So okay, so we've done the first part, actually getting video in. Now you need to get it into memory, and that's where the formatting stuff comes in. You have to specify what the format is of the video, how you want to get it into memory. Just because you're getting, say, RGB or YUV in, the pipeline may actually be able to do color space conversion and go from YUV to RGB, or basically do whatever you want. So typically you have a V4L2 format where you can set everything up what you want there. In a driver, you have to support. The first thing you do is actually call try video format. The try is just, okay, this is what the user wants. What can I actually do? And it will massage it to something that the actual driver can handle. So when you set it, you first call try to figure out all the little nitty-gritty stuff, and then you actually program the hardware and you set it up. You get the current one. What formats do you support? So you can enumerate what you actually have supported in your hardware. Yeah, this may, I'm not sure if, is that visible in the end of the room? Okay, so next time I give this, I have to split this up into separate slides. Right. I wasn't sure about it. I have already done it quite a bit, splitting it up, but this is clearly a bit too small. So I have here a standard function that basically sets up all the different format fields. So it checks what does the user want. Some things are just hard-coded because the hardware supports just one thing. Other things are allowed to vary. This really depends on what your hardware can do. So that's setting up. So you have input, selecting an input, selecting a standard, selecting the format, which is basically how you want to see it into memory. Next part is actually getting the data in, streaming. Video4Linux has a number of different ways of doing it. One of them is read, the old-fashioned read API, which is fairly limited. Actually, this is primarily useful if you're getting your video as, say, a compressed MPEG stream. Then just being able to read that data and pipe it to FFmpeg or whatever is very handy. But normally you use memory mapped streaming, so your buffer is allocated by the driver, you memory map it, then you can read it out. Or user pointer streaming, where you just allocate a user space, you give the pointer to it, and the driver will fill it up. That requires scatter-gather DMA support, which not all hardware properly supports, or may not support it at all. A recent addition is DMA buff, which allows you to actually share buffers between, say, graphics driver and Video4Linux driver. So we have Video Buff 2 framework for that, which is absolutely brilliant. There was a Video Buff, so let's say the first version of this, which is absolute crap. Don't use it. This is a replacement, and it's quite nice. So you insert a VB2 which is basically dealing with all the buffers that will be there for streaming. You need some allocation context, basically additional information that that particular streaming mode needs for your memory. It's used internally for pretty much the most part. And you need to take care of a few things yourself, which is basically a buffer list. So the idea is user space queues a buffer. First, that buffer is managed by the framework. Then that buffer is passed on to the driver. At that moment, the driver is responsible for it and has to set up the DMA engine so that it can be actually filled by your DMA. Once the frame is captured, it's given back to VideoBuff2 framework. VideoBuff2 can give it back to the user space when it asks for that. What it means is that the driver needs to have a list of buffers that it controls itself while it's responsible for it. That's this. So you have a log to maintain access, you have the buffer list itself. You also need to generate sequence counters for every frame, so you need a sequence counter. The buffers themselves, you need to have a VB2 buff, and after that you need to have a list as well so that you can hook it into that top level list. So, okay, the first thing you have to do in the probe function of your PCI driver is you take your VB2, take a pointer to that queue, and you say, okay, what am I going to do? I'm going to use it for video capture. What modes do I accept? Memory maps, DMA, buff, and read. Forgot to say that. So you include the VideoBuff2 streaming mode. So there are actually 3 different headers here: VideoBuff, DMA, config, which is a contiguous memory. So it's only for memory, cannot be used for scatter-gather. There's a DMA SG, which can be used for scatter-gather. And there is a VideoBuff vmalloc, which is typically used when, say, a USB device, you don't really have scatter-gather or memory map stuff. You just allocate a buffer, virtual memory. You just use that. So you have to, depending on your hardware, you pick one of those 3 headers, and then all the right stuff will be loaded for you. So memory map, DMA, buff, and read. We don't support user pointer here because that would require the scatter-gather variation. Pointer again to your skeleton structure, your top level structure. Set up the size of buffer. Pointer to, this is actually what you have to implement yourself, so that are the various streaming operations that you have to do. This is a standard pointer to, again, that comes in through the header. Those are memory operations for contiguous physical memory. So every time you have a different memory model, you need to set up different memory operations. 99% of the time you just pick the default one, but if you have really weird memory requirements, then you may have to write them yourself, which is not trivial. Timestamp, so when you get a frame, you will be timestamping it, and there are several ways of doing that. Normally, you will always use the monatomic timestamp. Again, that top level lock that I mentioned, so this is the lock that will be used for the streaming Ioctls. This driver assumes that your DMA engine can only do 32 bits. So if you have a 64-bit system, you have to tell it to allocate buffers that are in the lower 32 bits, which is this flag that you specify. Basically, whenever buffers are allocated, it will OR it with these GPF flags. So you can put in there whatever you need. And then you initialize it. This is, I'm ignoring this, not enough time. That will take care of most of what you need. So you need to implement your streaming operations. That is basically how you implement your DMA engine. And you have a setup that is basic. So what is the minimum number of buffers that you need? What is the memory requirements? I will show that in a bit. Buff prepare prepares a buffer for DMA. Buffer queue, that's actually called to pass the buffer from the framework to your driver. Start streaming, start streaming. Stop streaming, stop streaming. And there are some locking things. So if you have to wait for a frame to arrive, then because you're called with the serialization lock held, if you have to wait for something, you want to release that lock. Otherwise, everything else would be blocked. So that's what these do. This one prepares for waiting, and the other is called when the wait is finished. And you can implement your locking there. Now these two are standard functions that we provide. So if you use the locking mechanism provided by the framework, then you can stick in these boilerplate functions and they will do it for you. Then you have all the Ioctls that you implement for streaming. And lovely thing, hey, that's all VB2. This is all provided for you. If you use this, you just stick them in and everything will work. Same for the file operations. Read, mmap, pull. You don't have to do anything special. You don't have to do anything yourself. You just stick them in and it will take care of the whole hookup. The only thing that you really need to implement are these. And since streaming is hard, so all the memory management, all the stuff, if you look at the code, what is going in there, it's quite complicated. Actually, last week, I've been debugging on it and found quite a few bugs, so I posted a bunch of patches to fix it. It's not something you want to do yourself. If you look at all the drivers that do not use VideoBuff2 framework, frankly, it's crap. It's just too complicated for most people. Well, of course you can do it, but it takes a lot of time to do it really good. And what happens in practice, you just do it good enough for your use case. But you're not testing other things. You never test complete all the possibilities. So having a good framework that takes care for all those corner cases for you is just ideal. So one of the things you have to implement, the queue setup, primarily you need to tell it what is the minimum number of buffers that you allow. That's hardware dependent. Some DMA engines need at least 2 buffers in order to function. How many planes? So normally, say in RGB, it's just one plane, so everything is in one memory block, but the red and the blue and the green may be in separate memory buffers. So then you would have 3 planes. The size required for every plane, and you stick in a pointer to that allocation context. Not that. Then you start streaming. One thing that we discovered, as I mentioned, you often need a minimum number of buffers. Problem is applications cannot easily get access to that minimum. So they would, for example, queue everything, even though they don't have to queue all the buffers. What I recently changed is that if you try to queue a buffer and you have not yet reached that minimum number of buffers, then start streaming can just count is the number of currently queued buffers. If it's not enough, it will just return no buffs. And the framework will just retry the next time a buffer is queued until the right number is reached, and then start streaming is calling. If you look at drivers that don't use it, they either work around it themselves through ugly hacks, or it's just failing, or whatever. So this is now built into the system that if your count is not enough, you need more buffers, just return no buffs, and that's all you need to do in your driver. The sequence number for the number of frames you start streaming, so you have to reset it to 0. And then you have to do the hard work, which is actually starting up the DMA. I can't do that for you in your skeleton driver. That's your problem. Stop streaming, sort of similar. Stop the DMA, release all the active buffers that you still have pending. You just mark them. You return them to VideoBuff framework, marked error. And that's it. This is actually buggy. I have some patches for that, but not this code as such, but the way this is called. If you look at what I did last week, I actually made some patches to hopefully fix that. If this returns an error, not no buffs, but another error, then stop streaming is not called, and then these buffers are never returned. So it's a bit shaky. Buffer prepare. Here is a buffer. Prepare it for DMA. Basically, it checks that it is not too small for what we need. You set up the payload, so you tell the system, okay, I'm going to get 1 frame full of RGB data, so you set that up. Again, given the time, I'm not going into all the details. Buffer queue, this is where you actually add the buffer to your internal buffer queue. So buffer queue is the one that gives it to the driver. And buffer done is the one that gives it back to video buff framework. And the last part is an interrupt handler. So that's, I mean, you know, you set up your DMA engine, you get an interrupt when a frame is filled up. And what you do there is you have captured a new frame, you delete it from your internal buffer list, and as I said, you give it back to video buff 2, marked done. And you set up the sequence counter, you get a timestamp as well when you captured it. Finally, several operations, changing inputs, standards, timings, and the format itself, they are not allowed while you are in the streaming process. So you need to put in this check to these functions to return eBusy. Again, it has to, all these operations, they can actually change the format of the data that you're receiving, and while streaming, the whole pipeline is configured for a particular format and you are not allowed to change. That's why this is done. Phew. So that's streaming. It's a lot of stuff, but in the end, all you need to implement are these functions, and you have to initialize it. That's it. So one of the last things, really the last thing I'm going to discuss, there's the control framework. Controls are knobs that you change brightness, contrast, volume, MPEG, encoding, bit rates. Basically, it can be almost anything. Controls are very important in Video4Linux, and you need to be able to handle that. Some controls are atomic, so if you want to move your webcam, to do motor control, move your webcam to a particular position, you want to give X and Y at the same time. Control framework was created to take care of most of the shitty stuff that you really don't want to do in your own driver, because you never get it right. You have a control handle structure that you stick in. You have one single operation, set control, that is called when you actually have a new value, you need to program the hardware. We have events, so when a control changes value, you can send out an event to some other application that is listening. So you need to stick in these boilerplate functions for that. And well, then you just define your control handler and you define the controls that you have, and that's it. You're done. So the set control function is very simple. You just get the control that has been changed, you check the ID, and you actually make the change. Now when you define your controls, you give a minimum, maximum, a step value, a default value, so that's all handled by the control framework. So when the user space wants to change the brightness, the control framework will check that the value is within that range and clamp it if not. So end result is that in set control, all the checks have been done. You know that your control is a valid value. You don't have to do all the usual type checks and range checks and whatever. You can just concentrate on actually programming the bloody hardware. Believe me, hard enough. Lots of features. Particularly interesting is the cluster feature, where you can say that a number of controls can be clustered, meaning they are handled as if it was one big control. That's done for atomicity purposes. Validation is all handled. As I said, if a control changes value, you can subscribe an event to that so that you can listen, hey, this control changes. This is, for example, also used for HDMI hot plugging, so you can have an event when the format on an HDMI connector changes. You just listen to it, hey, something happened, I need to reconfigure my video pipeline. All done by the framework. Normally, most drivers, they just have one set of global controls. It is possible to have different controls for every video node. Say one video node is for an S video, the other is for an HDMI, and they have different properties there. You could even have it per file handle. Every time you open the video node, you can have your own set of controls that is used for certain memory-to-memory devices. And I'm skipping that. Oh, not that one. This is basically what I've been talking about. I could have put it up first, but then everyone would have left. Top level video device. It has a list of sub-devices and a console handler. Every sub-device, let's skip that because I didn't really talk about it, but sub-devices can have their own console handler. It has a number of video devices. Video device has a pointer back. List of open file handles. Video buff2 queue that is used for the DMA engine. And again, a control handler that it can have. File handle list has a list of open file handles. Every file handle can have a list of events, so people listening to the event that they want. But can a console handler has a list of controls. What can I say? This is basically the picture that we have been working on. And to give a good, so you go 6 years back, then this was the only thing that was there. All the others are all new, all added in the past several years. Few final notes. So I mentioned at the beginning in resources we have a number of utilities. Video4Linux CTL, Swiss Army knife, basically allows you to do almost any Ioctl that you can imagine. Video4Linux compliance, even with all these frameworks, is still complicated, so you need a check utility that actually tells if your driver complies with all the requirements. So there's lots and lots of checks. It's not 100% coverage, but we're about 90%, and I actually hope to increase it to about 95% in the coming 1 or 2 weeks. Debugging tool to get access to registers if you're root and certain other kernel configuration is set. A Qt test application that actually shows you the frame that you're capturing. We have some core debugging. If you set this to 1, you will actually see all the Ioctls that are being called. So, well, it was 4 hours. I managed to do it in 50 minutes. I skipped a lot. I mean, definitely not everything that we support has been discussed, but again, I thought about doing it for 4 hours, but then I decided against it. Questions? Don't ask about things that I haven't discussed, because then I will be here for 4 hours.
Hello? Yes.
Yeah.
The contiguous DMA support. How do you make sure you don't run out of contiguous DMA-able memory when using the framework? Because I assume, I don't know what happens to the buffer when you free it. Basically, normally you need to keep it allocated and locked in the memory.
Yeah. This is a problem that has been, at least for the most part, solved with contiguous memory allocator. Which is actually a way where you reserve an area in memory for large physical contiguous buffers. You can use it for other things, but when you request a large physical buffer for Video4Linux, it will move pages away from that area elsewhere, so that it will be allocated there. So that area is basically reserved only for movable pages or allocations like this. It's definitely implemented in ARM. I don't know whether there is a CMA implementation for Intel at this moment, but usually Intel, you have so much memory, it tends not to be an issue. Of course, if you're starting to use 4K contiguous video buffers, then you will run into problems there as well. But the trend in general for newer chips is towards scatter-gather DMA anyway. They are getting more powerful, they're now able to handle that, so it's probably a problem that will be gone in a few years' time. Other questions? There.
How do you deal with the device ordering problem? Is there possibility in UDF or anything else?
How the ordering, Are you talking about the sub-devices, how the device tree, how that is loading stuff, or just in general?
In general, I have
Right.
many devices of the same art, of the same kind, and I'd like to be sure that I'm talking to the right one.
Not really a good solution other than using UDEF rules. So you just know where things are which PCI slot things are, and then you can try to detect that and give them a fixed video number, or rename them to something that makes sense. For USB devices where it can all be plugged and unplugged at random times, other than checking USB IDs and do something special with if it's a certain type, you really can't do a lot there. I mean, it's just hot pluggable, you can't control it anyway. But UDEF rules is pretty much the only way you can do it, in general. No more questions? Okay, thank you very much.
Thank you very much.